Hi, I'm Femi OK, and you're in the stream. Scientists have discovered a new way of looking at our universe through waves of gravity. Today, astrophysicists answer your questions about gravitational waves. We are having a physics party today on the stream. You should see who are our guests of honour. Malika Bilal is pretending to be a physics teacher. I think the students are way smarter than the teacher, though.
I'm not pulling it off very well.
All right, what do you have?
Luckily, they come bearing lots of good questions, and we're going to have lots of good answers from them, for them, excuse me. And one of those answers comes from someone who's very excited about this discovery. This is Shane. Here's what he told the stream.
LIGO's detection of gravitational waves from binary black holes is the beginning of our ability to observe strong gravity and to compare those observations to general relativity. As we see more and more of these events, our ability to test and examine our ideas about the structure and behavior of space-time is only going to get better. This is the beginning of true gravitational wave astronomy.
So what that means is a whole new door of science has opened, and we want to take you with us. Tweet us your questions and your comments with #AJStream.
So gravity can exist in waveform, but why does it matter? Two black holes, 1.3 billion light years away, collided and sent waves of gravity that eventually reached our planet. For scientists, the discovery opens up a new field in astrophysics that could help us learn more about high-energy events in space and how our universe originated. The idea of a gravitational wave was first proposed by Albert Einstein 100 years ago. Listen to scientists react to the discovery in clips from the Laser Interferometer Gravitational Wave Observatory team, also known as LIGO.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of.
Can you feel the passion radiating off your TV screen? Wasn't that amazing? With us to talk about this in Cambridge, Massachusetts, Nergis Mavalvala. She's a member of the LIGO team and also Professor of Astrophysics at the Massachusetts Institute of Technology, also known as MIT. In Melbourne, Australia, Katie Mack, a theoretical astrophysicist. And in Los Angeles, California, our old stream friend Ian O'Neill, solar physicist and space science producer with Discovery News. He also speaks fluent science if ever we need some help with that. Hello, guests. Welcome. Great to have you here. Okay, Nergis, scale of 1 to 10. How excited are you right now?
Off scale.
Oh, okay. All right. Katie, for you, if you could actually put it into words, what would you be? Would you be a 10?
I mean, if 10 is as high as I can go, then definitely, yeah. It's unbelievably exciting.
Ian?
Yeah, it's historic. I don't think you can even put a measure on how exciting this is. It's confirmation of 100 years worth of theory from Einstein, and it's just mind-blowing. So, yeah, on a scale of 1 to 10, it needs 100.
I'm amazed that we can fit Nergis's head actually on the screen right now, Nergis, because you were part of this team. You must be so phenomenally proud. But let's start with basics. How did you even find the gravitational wave? How did you manage to measure it? Let's talk about the instruments that you use.
Yeah, so the instrument is really near and dear to me because, I and many others have been working on it for decades. So the instrument is something called an interferometer, and that's what the I in LIGO stands for. It's really quite simple. We measure the time that light takes to travel from one mirror to the other. And when a gravitational wave comes by, it actually moves the distances between mirrors, and that changes the light travel time of the laser. And that's really the principle of the measurement. If the distance between mirrors gets longer, it takes light a little bit longer to travel to the mirror and back, and we can measure that light travel time by comparing it to another beam that was going at 90 degrees.
So Nergis, you've said all of that, and now there's a simple question that may not have a simple answer, but this is Ali, and he wants to know, did you actually see the waves?
Yeah, so see is a very interesting word. Of course, we see it because what happens is that the light in our interferometer gets converted into a voltage, and that voltage is recorded on a computer and turns into a graph. So yes, we do see it. And if you could just put your eye where the light out of the interferometer is coming up, you would see laser light come out there, except you wouldn't exactly see it because our laser is infrared and our eyes don't fully see that. But really, yes, we register the signal and then we make a graph and we see it.
I'm going to play you a chirp and then Katie's going to tell us what we're actually hearing. Have a listen to this. Katie?
So that's the sound. So that's where you take the gravitational wave amplitude. So the wave is moving through the Earth and it's stretching and squeezing the space and it's moving the distance between those mirrors, and at different amplitudes. So it's moving a lot and then a little bit and so on. And if you chart that as the amplitude of that wave, how much the stretching and squeezing is happening. And then you convert that into sound, it makes that little chirp noise. So the first one of those, the lower pitch one, that's what it would have sounded like if you converted that signal to sound at the detector. The higher pitched is the one that sort of sounds better to us, where you could hear it really sounds like a chirp, because what's happening is the amplitude is rising and the frequency is rising, and so you have, it starts out sort of lower pitched because the waves are sort of going more slowly, and then it sort of speeds up and gets stronger. And when the black holes merge, you get the really strong, really fast sound, and that's the sound of the conversion of the waves into a sound, and that's how you sort of, by analogy, hear the black holes colliding.
So Ian, this has been going on for a long time, this search for gravitational waves and also gravitational observatories, gone back a couple of decades. When did you start to hear that there might actually be definite, concrete evidence that gravitational waves are out there?
Yeah, this is a cool thing, because I've been in science media now for around about 10 years. So LIGO has always been with me in my writing, and I've always been fascinated by gravitational waves, but LIGO just never detected anything. They were able to put limits on how powerful they think these theoretical waves could be, but they never actually detected anything. And so it was actually put online in 2002, and it underwent a massive sensitivity upgrade in 2010, and literally it just went back online in September last year. So it took 5 years to renovate the thing. And they really boosted the sensitivity of this detector. And so instantly when it went online last year, rumors started surfacing on Twitter that gravitational waves have been discovered. And of course, in science media, you don't tend to pay too much attention to the rumors, although you still write an article about the rumors, because why not?
Yeah.
And you examine it. Yeah, exactly. And you kind of look at the skepticism side, and I'm sure Katie and Nergis will talk on this. That there's been a lot of speculation surrounding black holes and a lot of rumors surfacing, and you've kind of got to be skeptical, and you think, okay, well, this sounds cool. So really last year was when I first heard that it could be a possibility. But then at the start of this year, we started getting more rumors, and then very specific rumors like 2 weeks ago about the size of a black hole merger. And this is the first time I was thinking, okay, this is a bit too specific. And then, of course, we had the big announcement last week. So we didn't have to wait for long, but it was wonderful to actually reach this point where the rumors were true. And in fact, the facts surpassed the rumors. The rumors weren't even close to the enormity of this discovery.
Nergis, I want to share with you one of the biggest questions that we got online, a question that I asked myself when I first heard we were doing this show, and that's this from Razi on Twitter, who says, how does one benefit from this new discovery? Now, there is a potential answer online. This is one person, Sulab, who says, perhaps does the detection of gravitational waves help scientists to understand the Big Bang theory more and understand creation itself? What would your answer to that be?
So I'll say to what Sulab says, yes, it's true. The detection of gravitational waves can help us understand the Big Bang, but we're not there yet. This generation of detectors is just not sensitive enough to see gravitational waves from the very early universe, moments after the Big Bang. Eventually, when we have detectors that are sensitive enough, we should be able to do that. But in the meantime, this discovery still has enormous, it marks several milestones. So the very first one is we detected gravitational waves directly. We can see the actual distortions of space-time with these detectors that have mind-boggling sensitivity. We've measured motion at the level of atometers. This is tiny. The second piece is we've discovered black holes that live as pairs and collide with each other. And that we've known. We've known black holes can exist, but we've not really known they can be this heavy, 30 times more massive than our sun. And we've never seen this unfold in real time, the process by which two black holes orbit each other, crash into each other, and give birth to a new, bigger black hole. And in that process, give off a huge amount of energy. So that's the second thing. The third thing is this is the first time that we could actually take a system like this and compare it to the predictions of Einstein's theory of general relativity. Now, general relativity has had many tests and it's been very successful, but there's one piece of it we haven't really been able to confirm, and that is this a theory that can describe those regions of space where gravity is really, really strong, like near black holes? And so it's very many things.
I'm going to slow you down just for a moment. Ripples in space-time. Explain that.
Yeah, so that's another really mind-boggling idea that comes from Einstein's theory of general relativity. Einstein tells us that empty space isn't just empty and just sitting around. It actually has properties, and one of the properties is that it can deform and distort when you put massive objects in space, and it can also ripple when those massive objects sort of vibrate or dance about. And in fact, that's the ripples that we're seeing right here in this animation. All of space-time itself is rippling. It's like dropping a rock on the surface of a pond, and the ripples spread out from where the rock was dropped.
So one of the things that I think is really exciting about this is that we've seen evidence for gravitational waves before from watching the orbits of neutron stars coming together and inferring that those orbits are coming together because they're sending out gravitational radiation, and that's taking some energy out of the orbit. So we've had evidence for gravitational waves, but this is just so much more direct, because instead of watching something in the sky moving around, we're actually seeing the gravitational waves coming and moving something on Earth, something that we built, and watching it be distorted by space-time changing, coming to Earth and really changing the shape of space-time here on Earth. And we're able to watch that in real time. It's kind of like, this is gravity, coming into your house and moving your stuff. Like it's really very, very direct, very sort of visceral. And the fact that we were able to measure it at all is amazing, because it's such a precise measurement. This movement of a thousandth the width of a proton, something like that. But it's also just, to me, it felt just so much more real than sort of matching what you see in the sky to equations. This is really like, we're watching the distortion of space.
You can actually see it. Ian, what were you going to say? Go ahead.
I was just going to actually ask, I had a few questions on Twitter, and one of the big ones that amused me was, can gravitational waves be used for evil? And I was actually going to ask Nergis whether this was the case. Perhaps we could generate our own gravitational wave fields and have some sort of Death Star situation in the future where we could blow up planets. I mean, and this kind of lends to another question. If they can be used for evil, how close can you get to like these gravitational wave producers before it actually hurt you? I mean, if you think about it, I mean, you're actually, if space-time is physically moving, I mean, could it injure you if you got too close to a radiating source? I don't know. It just kind of freaks me out a little to know they're going through me.
Nergis, do you have an answer for that? I have to say that the chirp does sound a little bit like Darth Vader.
Yeah. So let me just say, I don't believe we can harness gravitational wave energy for anything, good or evil. It's just too weak by the time it reaches us. Now, there is a lot of energy that's given off in gravitational waves right at the source. But right at the source, the space-time distortions are so extreme. I mean, it's a storm of space-time distortions that very likely, if we were too close in, would probably get ripped apart. So I think we're pretty safe for the moment if we stay far away.
Right. So let me just play this chirp because it really is Darth Vader. Hold on 1 second. Here we go.
Right. Another question here. This one is from Ahmed, and he says, if gravitational waves are ripples in space-time, how do they affect time where they pass? And can there be ones too big to detect? And Katie, I'll throw that one to you.
Yeah, so anytime space-time is curved, like for instance, when you're close to a gravitating body, like a black hole or a planet, that changes how you experience time in that environment. So if you're standing on the Earth, time goes a little bit slower for you than if you were out in the middle of empty space, far away from a gravitating object. So any curvature of space-time does affect how time flows. These are really small curvatures of space. I mean, these are ripples in space-time, and they are changing the curvature of space-time a little bit, but it's very small. So the time part isn't as noticeable as the part where space is being moved a little bit. And I mean, even that is just a really tiny distortion.
Let me throw some headlines out to you, Ian, and a couple that you've probably seen over the last couple of days. From Mashable, we finally found gravitational waves, so can we time travel? From RT, what if a black hole swallowed Earth? Scientist describes 3 possible scenarios. One more back here, which is, hold up, did we just crack time travel? What do you think we're not understanding as a general public that might not be science literate? What are we not getting here, Ian?
Well, I think the discovery of gravitational waves really gets the science fiction part of your brain thinking, because this is a very complex. It's a very, very complex idea, and I think it's up to the likes of me to actually try and communicate it in a more of a general way, because it all comes down to equations, and the general theory of relativity, Einstein's famous equation from 100 years ago, is steeped in very complex ideas about the universe. And Einstein was very well known for his thought experiments. He was very smart at recreating the universe in a very understandable way. So he was able to take his equations and turn them into models that we can all imagine. And space-time is one of those things. And one of the models that are often used by the media is like the idea that space-time is a rubber sheet, and any like a bowling ball is put on it, it bends space-time and it warps space-time. As Katie was saying, space-time can be warped by masses. And likewise, as Nergis said about the analogy of a rippling pond. These gravitational waves traveling along the surface of a pond, and like this particular event, and I think what's probably missed is just how ferocious this event is. And I think people kind of get a bit lax about understanding how big these black holes are, how big neutron stars are, how massive these objects are, how energetic these eruptions are, because this particular event that happened 1.3 billion light years away and billion years ago, in fact, was like throwing a brick in that pond. The ripples produced by this eruption were huge. They had for a moment, they had the equivalent energy output as all the stars in the universe times 50. So this was a huge event, and we're just feeling it now. And it goes to show how weak gravitational waves are, because it was extremely difficult to actually detect these waves. They're extremely faint. but they travel through space-time unimpeded. And this is why people are getting very excited about like looking into the dark universe, basically looking at black holes that are emerging that don't necessarily produce light, because of course astronomy uses light, uses the electromagnetic spectrum. So perhaps now we can look at gravitational wave astronomy. We've heard this being bandied around, but I don't think people necessarily understand what this means. We're actually going to see a gravitational universe like we've never seen it before. And I'm just really excited to see perhaps the first live map of the sky, all the gravitational objects that are producing gravitational waves. Like you've got your supernovas, you've got your merging black holes like this event. There's just so many possibilities, and I think we're kind of swamped in the possibilities. And everybody's saying, you know, how does it affect me? Well, you can argue, how has astronomy affected your everyday life? Well, it's affected you in many ways that perhaps you don't actually understand. So in the future, gravitational waves could completely transform our civilization as a whole.
Ian, you just kind of blew my mind there, because when you first started talking, I had some tweets that I was going to bring up about time travel, some questions people were asking about that. But then in the middle of what you were saying, you talked about how ferocious of an event this was. And so that led me to this tweet I just saw from Andreas, who says, what would have happened if the black holes were much bigger? And what would have happened to the waves? Another person picks up on that, and I see you nodding there, Nergis. Sonia, who is a member of the stream team, wanted to know, what are the chances Earth will get sucked in by a black hole? So can you talk about this ferocious activity that we saw?
Sure, I'll take a stab at that. So the first question is, what would happen if the black holes were a lot bigger or heavier? Well, what would happen is that the signal that we had detected would be at a different frequency. So we can tell how heavy they were by looking at the shape of the signal. So we would have gotten a signal of a slightly different shape and amplitude if they were bigger, but they would have been kind of a similar signal. And we're hoping in time that we will see a whole bunch of black holes that are a lot bigger than these and maybe a lot smaller than these as well. And then the second part of the question was, well, what if the Earth? What if the Earth got too close to a black hole? So here's a very fun thought experiment. You can come up with a scenario where you can crush our sun into a much smaller radius so it becomes a black hole. And in fact, the Earth wouldn't really notice. Yes, we would become very cold because the sun would stop shining. But in terms of our orbit around the sun, it would just keep going. And so I think black holes have, outside of the black hole, far enough away, it's gravity kind of like we know it. It's just when you get very close in that it gets a little bit energetic and distorted and scary.
I have never seen so many pictures of Albert Einstein in my life as over the last couple of days. This was one from Princeton University Press, and it has the trending hashtag Einstein was right. And then this, Ian, I don't know if this is your house. This is definitely your tweet. Oh, Albert, what a day. What a day. And then there is Albert Einstein. What does this tell us about Albert Einstein, who's been dead for a very long time now? But what does this tell us about him? What do we learn more about him by finding out about gravitational waves? For sure.
He's looking down on us right now, listening to all this. Basically, it confirms Einstein's general relativity, theory of relativity. And everybody says, it's just a theory. Well, it's not actually. It's a description of a lot of very solid observed evidence. And general relativity is used in everyday life. It's used for instance, like the GPS satellites that are in orbit around Earth. There has to be a slight time correction, which is predicted by Einstein's theories that were put together 100 years ago. Now, if you go back 100 years ago and speak to Albert Einstein about his theories and how it might have an application for
what do you
real
think?
life.
What do you think he might have said, Ian? I'm right at the end of the show here. What do you think he might have said?
Told you so.
Excellent. We're going to take Ian and Katie and Nergis and you to our online post show at stream.adzero.com. We're going to talk about gravitational waves a little bit more there. But I just have time to say this has been a Kylene Kiang production. Kylene has been on the stream since the very beginning of the stream. She is leaving our team. I want to say a very big thank you. Only Kylene would have done a show about gravitational waves. Kylene, we thank you. Thanks for watching, everybody. Hello again, this is the Streams Online Post Show, and we're talking about the discovery of gravitational waves with Nergis and Katie and Ian, who've been doing an excellent job of just keeping the momentum going and actually making me want to do even more research than I've already done, which was a lot. Meanwhile, what else do we want to talk about? Now what?
Exactly, the now what, and some of the potential future applications for this. This is a tweet we got from Dennis, and Katie, I'll direct it to you. Dennis says, technical ability given, could this discovery be used for faster space travel?
So I've gotten a lot of questions about whether this can be used for space travel, for time travel, things like that. At the moment, all we can really do is watch. We can detect the gravitational waves. We can see what's going on in the distant universe in these really violent events like mergers of black holes. But at the moment, we really don't have any way to harness that energy. And it's a very weak effect. The gravitational waves are very weak. It's very little energy that we're receiving. So that's not something that we can do at the moment. Whether or not understanding gravity better will lead to things like better space travel or some kind of ability to harness gravitational energy in some new way in the future, that's impossible to say at the moment. But as we study this stuff, we'll learn more about space, we'll learn more about distant objects in the universe, we'll learn more about gravity, and that'll help us to develop, potentially better theories of combining gravity and quantum mechanics, theories of everything, things like that. So at the moment, it's not something we can use for a practical application, but you never know how these things will turn out in the end.
See, Kelly, that was a very kind, polite answer, because when that question was being asked, I could see Nergis out of the side of my eye going, no. What's wrong with you people? Keep up with the science.
No, actually,
I'm interpreting that.
I should say Katie's answer was spot on. We really just don't know yet.
Right. Good. That was a kind answer. Any other questions that you're being asked right now? We can do this as a group think, group mind, where you're like, that is a dumb question. Stop asking that. Do you want to do like a go round table? Ian, don't ask this question about gravitational wave. What should we not ask? Because it's silly.
I don't think there's been any really surprisingly actually. There hasn't been any like what I would consider silly questions, but probably one of my pet peeves. And Katie will back me up on this. A lot of media and even some scientists, this is known across the board. Everybody does it. Is confusing gravity waves with gravitational waves. So gravitational waves are ripples in space-time. Gravity waves are an atmospheric phenomenon which actually happens. I can probably look out the window and I'll see some clouds in a funny wavy pattern. Those are gravity waves. So let's make sure we get that straight.
Whoa, that's really important. Okay. Yikes. Katie, any pet peeves on this topic where you're thinking, oh man, I wish everybody was a bit more science literate?
Nothing like that, but one of the questions that I've gotten a lot is, what's in this for me? How does this make my life better? And I think that's a valid question. I don't think that's a bad question, but I think that also, I think a lot of people don't always realize that when we do really fundamental science like this, that doesn't have any direct applications right now, that, it tells us more about the universe, but can't, make a car go faster. That kind of fundamental science, it really does often lead to really, really important technology down the road. I mean, we had that with, studying antimatter gave us PET scans, studying general relativity. Now we can use GPS systems and know where we're going when we're driving. So all of those kinds of things, doing this basic science is super important for stuff we don't even know that we need, that is going to change our lives down the road. So I think that it's important to understand that fundamental basic science that has no practical application is a really important thing to pursue. And just because we can't see how it's going to change our lives now doesn't mean that it's not going to do it.
Katie, I'm so glad you said that because it's kind of echoed here on Twitter. This is Amy, and she says, this detection opens up an entirely new way to measure the universe, and it's a true testament to the dedication and the perseverance of the scientists and the engineers who've been working so hard for so long. So, Nergis, I'm going to go to you with that because we also got this tweet, and we saw a couple like this. This is Yawar, and he says, Nergis was born in Karachi, Pakistan. So proud of you. Gravitational waves is the hashtag. You've been doing this for 25 plus years, and now that this has happened, what's next for you?
we've really just touched the tip of the iceberg. So we have plans for making improvements to the detectors. Look, every time we make the detectors a little bit more sensitive, we can look at fainter objects, or we can look farther out in the universe. And so we're just going to keep doing that till we can do what Ian dreamed about, which is to map out the entire sky in gravitational waves, near and far. And so I think the work is just begun for us. This is really just the very first time we got these instruments running to be sensitive enough to see something, and now we just keep going.
See, Nergis, I don't want to make you blush too much, but here's another tweet that we got here. Pakistan's gravity girl, #Nergis Mavalvala, and you were trending. You were trending. Not just Einstein was right, but you were trending as well. What is that like, the trend? In a good way.
Totally embarrassing. This is the effort of a huge team, and I'm privileged to be part of the team. And so it's a little embarrassing to get so much personal attention.
I'm looking here, Ian, at a map at gravitational wave observatories around the world. And if you can look at the yellow ones, these are ones that are operational, green under construction. And then we've got a planned one that's in India. So what does this mean for the future? Could we see sort of announcements every couple of years and more amazing physics being revealed to us?
It will be exciting, and now it's been confirmed, because up until now, I mean, this is a testament to all the engineers and scientists who've been involved in the LIGO project, because they've had so many years of no detections, and of course, in the world where science is driven by politics and public opinions, when you start hearing this multi-hundreds of $million project not producing gravitational waves, people are like, oh, obviously they're not on the right track, but they persevered and eventually they found them. So this is like a generational discovery. And so everybody around the world is now thinking, okay, well, gravitational waves do exist, thanks to LIGO, thanks to their tenacious attitude and actually forcing through and actually discovering these gravitational waves. And I've just heard that China's talking about setting up their own gravitational wave observatories, and they're going to throw a lot of money at it. So that's exciting. If we can have a worldwide collaboration of gravitational wave detectors who will be able to pinpoint where these objects are, where these gravitational wave generators are around the universe, and as Nergis said, we'll be able to have that map of the universe, which could be as profound as perhaps discovering and mapping the cosmic microwave background radiation, which is the echo of the Big Bang, and that was profound. This could even be more profound. We're actually going to see an invisible universe we've never seen before.
I have a black hole question.
If I can...
Yeah, go ahead, Katie, go ahead.
Sorry, if I can add to that. Once we have more than 2 detectors running, we'll be able to really precisely tell on the sky where something is coming from. So we'll be able to know exactly where the black holes are colliding, or if we see neutron stars colliding, we'll be able to see where those are. And that'll be really important for astronomy, because then we'll be able to check for counterparts of that event in electromagnetic waves. So for example, we think that when 2 neutron stars collide, that can produce something known as a short gamma ray burst, which is a quick burst of gamma rays in the sky. And we'll be able to test that, and we'll be able to learn about how stars are born and die, and we'll be able to see something, we'll be able to see the light coming from something and the gravitational waves as well, and really see how these massive objects are affecting space-time and very directly. And that's going to be amazing from an astrophysical point of view.
Who's the expert on black holes? Who wants to take a black hole question? Don't all yell at once.
Is there anybody who's an expert on black holes?
That's the whole point. All right, so this is from Kylie, our producer. So she says, supposing there's a black hole anomaly, so the black hole effect, could that affect gravity down on Earth? Could it have any impact on us on Earth? Is that possible?
Well, I mean, so if there's a black hole in space and it's colliding with another black hole, obviously we can see the waves from that as we've done.
Yeah.
But in terms of the gravity of a single black hole directly affecting us, we'd have to be pretty close. I mean, one of the things that is a sort of misconception of black holes is that they sort of suck in everything around them.
Yeah.
You actually have to get pretty close to a black hole to be strongly affected by it. You have to get close enough that the sort of tidal forces of where the gravity is changing really, really quickly can mess with you.
Right.
If you're far enough away from the black hole, it doesn't seem like anything odd. So for the most part, black holes are pretty benign, and there are none close enough to Earth to be a problem.
Okay, yeah, because our team was like starting to get scared about maybe we could get swallowed up by a black hole. On my list of worries, that was not on my list, but my team were concerned. Malika, what do you have?
I'll close with two tweets. One, after watching the show, this is Dennis, and he says, thank you for this show and for reminding me I would have chosen a different career if I wouldn't have been such a zero in math. He's not the only one. I feel the same. But this last one from Andrew pretty much sums up what a lot of people online feel, and that is that today the nerds are winning. Hooray!
Yes.
So Nergis Mavalvala, and go ahead. You go first.
We're all really excited. Everybody I know who's even remotely connected to physics has just been giddy for the last week. It is a profound victory, and we're all really happy about it.
You can find them online. Nergis Mavalvala, Katie Mack, Ian O'Neill. Thank you for being part of our show today. This is our normal music, but I don't want to play our normal music. Katie and Jeff, I want to play the gravitational wave chirp from LIGO. We're going to play out with this. Thanks, everybody.